Alrighty guys, welcome back to this third video actually. So today we're going to be talking about Internet Protocol IP. Okay, the agenda is to go through the IP header fields and understand IP fragmentation. Okay, so this is a topic that is going to have a little bit of depth to it. So don't shy away from that, but we're going to uncover it all today in the video. So next slide. So the role of the network layer, this is what we need to understand in order to understand the Internet Protocol. Okay, so the internet layer is where the administrators usually do the most network configuration. This is the layer where the IP protocol operates, and it's the heart of the TCP IP protocol suite. Okay, the network layer is responsible for four main tasks. Okay, so there's four of them: defines and verifies IP addresses, routes packets through an internetwork, resolves MAC addresses from an IP address, delivers packets effectively. Okay. Now, on the right, I've got the OSI model, I've got the network layer, and in the last lesson, we went through the acronym, which is PDNTSPA. Please do not throw sausage pizza away, if you remember that from the last one. Anyway, next slide. So, the role of the network layer. IP address is assigned to all computers and network devices using TCP IP for communication. So the TCP IP is given, it's a protocol which is used, and it's the communication protocol which all devices must use in order to communicate. Okay, IP addresses have two functions. Now, an IP address, I haven't shown a picture of what an IP address looks like yet, but we'll be going into that. For now, just know that it's a bunch of numbers that represent something. Okay, and we'll go through that. What it's used for is to identify a network device in an internetwork layer, identify the network on which the device resides, so that's the network. If a device gets an IP packet, it is processed, and there's two things that happen. If it matches the device or the network, or it's a broadcast, the packet is processed. If it's not a match, it's just discarded. Okay, so if it's not related to it at all, it's just discarded. All IP addresses have two parts that make them up: the network ID section and the host ID section. We call them the portions, so the network portion and then host portion. Make sure that's on. Okay. Is that on? Okay. So the broadcast IP address is a special identifier used to send data packets to all devices within a specific network, ensuring widespread communication. And functionality such as ARP requests and DHCP. So ARP is address resolution protocol, and then the other one is dynamic something. I forgot. I'm gonna have to go through that one again, but we'll go through the protocols later. Anyway, protocols at the network layer, commonly used ones are the IPv4 and IPv6. I made a mistake there in spelling. ARP, IMCP, and IPsec. Okay. IPv4 and IPv6, the main differences are when they were invented and the amount of devices that can reside on the network. Okay, so you've got a lot more potential addresses that can reside on a IPv6 network. Yeah. So you've got 340 decillion possible addresses, and then for IPv4 you got 4.3 billion. And as you know, everyone has a device, so we've already kind of used that up nearly. Now, IP header in depth. So this is the IP header. I think we went over that before in the last one, but we didn't go into detail on it. Okay, so today we're going into depth about what it is, each compartment, each section. So keep this table in reference. This is basically what is sent, the information that is sent when a packet is sent, and this is the information that comes with it. Okay, and it's called an IP header, and we're going to go through it. So remember that, and we're going to go through this. And here is a visualization of the data in a sort of relation to like an analytical thing. So we've got, maybe that's Wireshark, which is a software to analyze packets, and you're just kind of like linking the different systems there and the different sections. Okay, so time to live is down here. You've got version 4 IPv4. You've got header length here, etc., etc. Or header length, sorry, is there. Okay, so the header length is obviously there, and then you've got source, destination, etc., etc. Now, but we're analyzing it through this visualization because on a computer, you do use this visualization, but we're going to be using this one up here at the top. Now, IPv4, IPv6, that's in the version field. Header length field is responsible for the header length of the header only. You've got the differentiated services field, which specifies priority and informs routers the level of priority they should process the packet, the incoming packet. Okay. You've got total length field, which is the total length of the IP packet, including header and data. So that's going to be everything that's included in the header and the data, the IP header and all the thing, everything combined. So it's obviously going to be a lot bigger than just the header value. You've got the identification field, which is a unique ID value that is sent. So basically, if you're sending multiple packets and you need to reform them together, you have to have the same ID so it knows which one's what, okay? So if a packet is fragmented, same ID number is placed in each fragment. So for example, if it's 1444 and there's 8 packets that need to be sent, all of them will have the ID of 14444, okay? You've got the flag field, which is a 3-bit length field. Specifies fragments is allowed or not indicates a packet is fragmented, and if it is fragmented, whether the packet is in the last fragment, first bit is unused, D is do not fragment bit, M more fragment bit, okay? Next one. We're going to need to understand MTU, which is maximum transmission unit, in order to understand what I'm going to show you soon, because this is basically how much information can be processed on the network. So it's the limit in which data is processed on the network, okay? So I'll read the description here and what fragmentation is too. Fragmentation is necessary for data transmission as every network has a unique limit, i.e. the maximum transmission unit for each size of the datagrams that it can process. Now, datagrams is the packets that are being sent, okay? If a datagram is being sent that is larger than the receiving server MTU, maximum transmission unit, it has to be fragmented in order to be transmitted completely. And I said that before, fragmentation is basically, if something's too big, information you're trying to send, it will fragment it into sections and then, or packets, they say. And then it gives them the unique identifier of the same number. And then we'll use different fields to identify and sort it, okay? And that's the next slide. Which is the fragmentation offset. Shows where to place packets data when fragments are reassembled into a single packet. The offset of the data is in the original datagram measures in units of 8 bits. The first fragment has an offset of 0. It only records the first byte number of that fragmented packet. Now we're going to go through examples in a second, but here are some issues with fragmentation. You've got overhead, you've got time and resources, you've got allocated memory, so you need to have all that. You've also got, if one of the fragmented datagrams is dropped, then the entire datagram must be resent, okay, of the entire original datagram. Alrighty guys, so I forgot to go over this one in detail before yesterday, but we're going to go over it right now. So this is the IP fragmentation and reassembly, okay? So we have a 4,000 byte datagram, which is specified right over here. This is what it looks like in a singular sort of packet. Our MTU is 1,500, which means we can transmit 1,500 at a time. Now, as we know before, the header has to have a 20 byte amount, so that means the data field has to be 1,480, as you can see here in the byte section. So what that means is this packet is going to have to be broken up into a few parts. So I'll pull up the calculator. Now, if you go 1,500 times 3 times 2, so times 2 doesn't work. So there's going to be 3 packets. So we can already know there's going to be 3 packets. The last packet is going to have less information. Okay. So if you look at this, you've got 1,500 plus 1,500, which is 3,000. And then if you add, you have to add some extra onto that to then get to 4,000 bytes for the datagram, okay? So we already know that it's 4,000 bytes, the datagram, which means that there's 20 bytes of information in the IP header reserved for that one. So there's actually 3,980 of data in that one, okay? So we need to match that in terms of the rest of the bytes, okay? So how can we do that? We can go, we're going to go here for the data. So we're going to look at 1480. So 1480 times 2, which is 2,960.
which is going to be the data length of these packets here. This is for getting the IP header because we can calculate that later. So obviously it's 20 here and 20 here, but we're calculating this length so far, okay? Now, from that, we can then decipher what's the remainder left over. So as we've established, how much we've left will be this amount that I've got here. So 2,900, and then you're going to take away 3,980, but it's going to be the reverse flip, so it's not a negative number. So let's do that right now. 3,980. So that's 1,020, right? So 1,020, meaning we have to do a plus 20 for the header field, the header IP header length it's reserved for the information, and that's going to equal 1,040. On my calculator, I have it right here, 1,040. You can see that here. So does that make sense, guys? It's basically you're fulfilling the rest of the data that's been broken up, and maybe the last packet has to have less information in it. In most cases, it probably will, because it's probably not going to be exact, how much is going to be sent. But as you can see, the first two have the same amount of length. The last one is just filling it up to reach the rest of the datagram so they can then reassemble that. Now, if you look here in the offset, this is just saying that this one is the second packet is starting at the 1,480 byte. 1,480, yeah, so section of data. And the next one is going to be working from that one. There we are. So this is the 0. This is starting from that reference point. This is starting from that. It's just saying where it's starting. So this is going to be here, here, here. So it's hard to like say it. It's more easy to visualize it. Does that make sense? So you're starting 0, 185, 370. Now they just mean where the data ends. And so like 480 here, 480 times 2 is then going to be the 371, because we're using in byte form, so it's easy to understand. So it's just we're dividing it by, so 480 divided by 8 is going to be 185, and then 1850 times 2 divided by 8 is going to be 370, which is over here, 370. So that's what you're starting next, the next piece of data, okay? So that should make sense. That's why it's 0 for this one, because you're starting 0. This one's starting from where this one, the first one ends. This one's starting from where this one ends, okay? And then, yeah, that reassembles and makes that packet / datagram up there. You've also got an ID, which is X for this example, and a flag, which means 1, which means there's more to come, 0, which means it's finished, okay? That should make sense. I'm probably not the best at explaining it. There's plenty of videos on that. I will link them down below. But the main premise should be understandable with what I said. You're basically fulfilling the data which has been given in the datagram in broken up sections, and obviously the last one is going to be either the exact amount or less to fulfill that exact amount which has been given to you, okay? For example, if the datagram was a bit bigger, like 50 more bigger, then this length would be a little bit more bigger down here. Does that make sense? But these lengths would stay the same because they're reaching the max MTU, which is the maximum transmission unit, okay? And obviously this one has a fair bit of way to go to reach the maximum transmission. But that should make sense, guys. On to the next part.
All right, so to finish this off, we've got the IP header fields and functions. Time to live shows the remaining life of a packet. You've got the protocol field, which says if it's TCP or UDP. We'll go through the details on that one later. That's not relevant right now. You've got the header checksum field, which tells you if the file or information has been corrupted during transmission. The source address field, and then the destination. So that's an IP address right there. So the source is going to be if the computer's sending it. The destination is where it wants to go. Okay. All right. So the next topic we're going to be doing IP addressing. This is going to be more technical, I guess. We're going to be doing more numbers and playing around with that and like binary and conversions and all that stuff. So stay tuned and enjoy that one.